So John invited me to give a talk on binary on tests of gravity theories and neutron star mass measurements with Argos, and I was thinking about this for a while, and it's actually not without having actual TOAs and knowing the sensitivities. It's actually a little bit difficult to estimate what would be the impact on the of Argos on those particular topics. However, there are a few topics where I think the impact is much more obvious, and I'm going to mention three of them here. One of them is the existence of many hidden binaries in our among the currently known pulsar population in our galaxy. I'm going to mention some of a few cases, that all of which turned out to be very interesting. Then timing of long period binary pulsars, and then mentioning triple systems. So hidden binaries are isolated pulsars, or pulsars that we think are isolated, that then with the continued timing turn out to be binary systems. One of them that is really interesting is this system PSR B1820 plus 02. So this was found about 3 years after the discovery of the first binary pulsar, 1913 plus 16. It's not as famous, of course. It didn't cause a Nobel Prize to be attributed to anyone. But although the Nobel Prize winner is there, Taylor. So it was one of the pulsars found in the Molonglo survey. This was at the time, so in 1978, so about 10 years after the discovery of the first pulsar, there were already about 300 known pulsars, and most of those, as you can see from the numbers, had been found in this particular survey, the Molonglo survey. But yet, so this was the second binary pulsar known, but yet if you look at the paper, you won't see any evidence of this. This is all the timing parameters here. You struggle to see any difference. So there's a weight 20 minus weight 20 minus plus 0.2 is there, but you wouldn't be able to notice the weight 20 plus 0.2. It's classified, it's cataloged as an isolated pulsar. And the reason for this is a very common one, is that many of the pulsar surveys, it's actually what we do, particularly the Parkes multi-beam survey. You find so many pulsars that you have to measure their parameters, the position, not proper motion, but position, period derivative. And you do this for about a year to get solid parameters for solid measurements for these parameters, and then you quit. And this was done for a vast majority of isolated or vast majority of slow pulsars. In this case, though, they fortunately continued timing it, and by 1980, it was quite apparent that the spin period of the pulsar was not just decreasing, because if you look at the initial stages, you see you see a change in the spin period. But then it turns around. So there's you can try to fit, of course, all kinds of timing noise to this parameter, but here the amplitude of the signal is such that it became clear this was a binary system. They continued timing. They continued following the system, and by 1983, they were able to finally, after very persistent timing, they were able to measure the orbital parameters and get a proper timing solution. And so they realized retrospectively that this was the second discovered binary pulsar. There was another one, 0655, that was found at about the same time. Anyway, the interesting thing here is that, and I'll come back to this, for this timing solution to be determined, they needed to do VLBI measurements in the same paper. And you can see here that there's a VLBI position. And this is very important because it gives us the additional information for the phase connection. There are a few other examples, not many, but all these other examples are very, in my mind, very interesting. One of them that I find that's remarkably quite remarkable is this pulsar J2032 plus 4127. It was one of the 16 pulsars found by the gamma ray pulsations alone. So this was 2009, as you can see. So this was very soon after the launch of the Fermi satellite. So they saw these very bright gamma ray pulsations. And then later, of course, people immediately said, okay, if we have these bright or gamma ray pulsations, we have gamma ray emission, we have radio emission. And indeed, for two of them, in this paper by Camille et al. In 2009, the gamma ray, radio pulsations were also determined that are also occurring. So it's a gamma ray pulsar and a radio pulsar. And then continued timing, in this case, motivated by the need to keep the radio ephemeris for better folding of the gamma ray photons, led to the realization that this is a binary pulsar. But this happens years later. So this pulsar is orbiting a 15 solar mass BE star, which had this catalog name MT911313. And it's now known, after a lot of effort, that this system actually has an orbital period of about 46 years, which is it's much larger than any binary pulsar known at the time. There was, and it was quite interesting that this was done at the time, because it happens that there was a periastron happening in 2017. So it was really good that people realized this before this periastron. Next one, it will have been about 40 something years. So this periastron led to a huge amount of X-ray follow-up in X-rays, optical gamma rays, and so on, that really allowed us to learn a lot about this system. These systems, by the way, are quite common. The implication from this kind of work is that they could be more common than we think if we look carefully at all the isolated pulsars. Another example that I should mention here, and that's what the figure is about, is this 1024 minus 0719. This is an isolated millisecond pulsar. The interesting thing is that it was found also in gamma rays, and this pulsar is being timed for PTAs. So that's one of the reasons, two reasons why it's being timed continuously, not only for the need to maintain a good ephemeris for proper folding of the gamma ray photons, but also because it's a PTA pulsar. And in 2016, we realized that there was actually a second large spin frequency derivative, and that this was not only that, but it is in a common proper motion pair, and that's what the figure refers to, with a particular 0.5 solar mass K-dwarf star. And the thing is, if you put all this information together, you get to an orbital period of a few hundred to a few thousand years. This is should become clearer now. So now there's a few more years of data. So these higher spin frequency derivatives, their precision increases very fast with the timing baseline. So the situation should be clearer now. Should be clearer now with for this particular system. But this is just an example of a very unconventional binary that we realized it was a binary because there was some needs in these two cases, motivation for related gamma rays and the PTA, that made people keep timing it and then realize, oh gosh, we have a binary, and it's a really, really interesting one. So the thing is, as I said, I mean, I'm mentioning that this possibility that some of the known pulsars are in binaries. Of course, it has been a topic for quite some time. I really refer people to this particular paper, which I find very interesting. Came up in July this year, and it emphasizes this point that you could have several or many hidden binaries. And some of them could even be pulsar black hole systems. So this is something that, so following a large number of apparently boring pulsars, we might hit a jackpot. So this is a paper that I really recommend people follow in detail. So yeah. So yeah, so to summarize this part, I think continued timing of many normal pulsars, particularly systems that have only been timed for a year or so, will no doubt reveal many, or at least several new binaries. And of course, you also do a lot of single, find out all kinds of other stuff like glitches, timing noise, nulling, intermittency, etc. Okay, continuing in the top of long period pulsars. Sorry, I'm pretty sick. So for isolated pulsars, we have here the parameters that we measure for an isolated pulsar, and these the timing signatures of these objects, and this is from the handbook, have time scales of 1 year and longer. So the spin and the spin down, of course, are very long time scale, and then you have the Earth's orbit. One consequence of this is that, I mean, this is a paper, by the way, of which I've been a co-author, where I helped find the timing solutions for several of the gamma ray pulsars, for all of them in this paper. And it has been quite difficult to find for some of these long period binaries a proper timing solution. So the phase connection can be very difficult. In the case of 0820 plus 02 that I mentioned, we needed the VLBI localization. This is important because if we fix the position, it eliminates the covariance with other orbital parameters. Another solution is the use of automatic phase connection, as in the case of the Dracula software that I wrote a few years ago. This really helps us connect many pulsars, but still, even with that software, connecting some of these very faint pulsars that we're finding, for instance, in this is a particular case. This is Arecibo discovery of some faint gamma ray pulsars. So if you are Arecibo and you're looking at Fermi-lat sources, you're going to find some of them are going to be super faint and cannot be timed easily with any other telescope. But of course, Arecibo was also itself relatively limited. And the thing is, when you look at some of these pulsars, because they're faint, they're fast spinning, and they're faint. So in between two different observations, you can have a very large number of rotations because the rotational period is short, and the uncertainty in the timing is relatively large because of their faintness, and some of them have very blunt profiles. So these systems are very hard to connect, even using this automatic phase connection. So better cadence here is obviously something very beneficial that I hope will help us connect other systems in a more efficient way. And this is, systems like with Argos. Another thing related to long period binary pulsars is that if we have a binary pulsar that you kind of know it's interesting, it has an orbital period of a few days, it's generally possible with a large telescope like Meerkat or Arecibo or some other, or Effelsberg, to GBT, to get a smaller, relatively small timing campaign where you can really sample an orbit very densely, and therefore measure things like Shapiro delay, measure the projected semi-major axis, and do all of these things. But this can only be done for if you have a wide orbit, and in this case we had this is 1903 plus a 327. This is a very wide orbit, and in this case we could only do it because we knew the orbit is not circular, as you can see on top. So the orbit is obviously unusual for a millisecond pulsar. This system is actually extremely unusual. It has a one solar mass companion, and it has eccentric orbit. It's probably a disrupted triple system, and and by doing these very massive investments of time, and we were able to measure the Shapiro delay, and we measure the things like the periastinal advance. in any case, repeating campaigns for these objects is simply beyond the time availability of many telescopes. I would say even if the pulsar is in a PTA, because PTAs have a problem, is that for many of them, the cadence that you can do is like 1 month. So to sample well the Shapiro delay area here, you need observations for a couple of weeks at least, and almost every day. So this is obviously a problem. So even PTAs cannot do this properly, and they don't actually. Many of the masses in some of the PTAs, like nanograph, for instance, you see the latest paper, and many of the masses are ludicrous. Like you get 3 plus or minus to 1 solar mass for some pulsars and so on, and actually for this case, which is well measured from omega dot, they get 0.9 solar masses, and they actually, they acknowledge that this is not the purpose of the PTA, is not measure them, and they cannot measure them properly. So another aspect on this is that understanding the orbital dynamics actually, and has been a contention that I've done for a while, it's actually important for the PTAs themselves. It's one wonders to which extent some unknown orbital effects might be percolating that are not taken into account in the solution, might be percolating into the gravitational wave background signal. Anyway, another thing that I think is important to notice here is that if you look at that Shapiro delay signal there, and if you have measurements here every month, and not too many of them, you could easily miss that peak, and lose some obvious Shapiro delays that might still be present somewhere for some of those wide binaries, is that we don't see them because don't have observations at the right orbital phase. So obviously there's in this case we measure it, and of course we can do some interesting tests of gravity theories with the system. We measure the precessional periastron, we measure the Shapiro delay. They all agree very nicely here. So it's not but this is a case where we really need better for more of these wide binaries, you really need better coverage, even to measure things like x dot and omega dot. So variations in the orbital parameters caused by the proper motion of the system. Another thing that I think is really important here is in the triple systems. So the triple system is very important to test the strong equivalence principle. The strong equivalence principle is a kind of a very fundamental concept that's only fully embodied by general relativity. Most theories of gravity, alternative theories of gravity nowadays, have obey the so-called Einstein equivalence principle, which is that if you're in a free-falling reference frame, the thing is everything behaves as if you are in a Minkowski metric. So it's as if gravity does not exist, which makes sense, because if you have some kind of curved space-time locally, of course it always looks flat. So this is a general feature of gravity theories that is explainable if you have a metric theory of gravity. However, if we go to the strong equivalence principle, then things change completely. So while most alternative theories of gravity predict the same results it's the same acceleration from different particles in a particular gravitational field, the story is not the same for self-gravitating objects. And just to skip ahead with this, for instance, this has been tested since the 1960s with the lunar laser ranging, where you measure from the Earth, send laser beams to the moon, and there's some reflectors there that give you bounce back. You can test whether the Earth and the moon fall with the same acceleration in the field of the sun. And traditionally, you also have the neutron star and the white dwarf. You test them. You test whether they fall with the same acceleration in the field of the Milky Way. If if they don't follow the same acceleration, then you have an effect called the Nordtvedt effect, which is you'd have a polarization that constant polarization, so a constant elliptical element of the orbit that seems to trail the other object. In this case, the sun, or in the case of the Milky Way, something that would not precess with the orbit with the normal omega dot of the binary. So there would be an element of the eccentricity that would stay pointed at of the eccentricity vector that stays pointed at the direction of the external polarizing field. This is called the Hughes lens vector. So the eccentricity, you can think about it as a vector, E times cos omega and E sine omega. So this vector, there's a component of this vector that always has the same orientation, which means like you get a varying, an uneven change in the omega with time, and an uneven and a change in the eccentricity. A better solution to this, so both these tests have problems. One of them for the Earth and the Moon is that the Earth and the Moon have very small binding energies, so they give you a weak test of the strong equivalence principle. The neutron star is much better, but the problem is that the Milky Way has a very small polarizing field. So that's why in 2012, myself and Norbert Wex and Michel Kramer proposed that you could do this test with a neutron star white dwarf if it's in a triple system. And actually, the better cases would be if the second object is a neutron star itself. Sorry, if the third object is a neutron star itself. Anyway, something like this, of course, had already been discovered. We're just, thinking about what the implications of this. This was published, so we have the triple system here. You probably already know about this system, just published by Ransom et al. In 2014. And our predictions in 2012 that this would be a fantastic system for tests of the strong equivalence principle were confirmed by Archibald et al. In 2018, where we measured that the differential acceleration of neutron stars and the white dwarfs in an external gravitational field is less than 2.6 parts in a million. So this is probably one of the best tests of gravity, general relativity that there is. We've done the same thing with using Nancy data, and it's a 2020 paper led by Guillaume Voisin, and here we actually improve a little bit, so we have a much better equations of motion that don't specifically assume general relativity. So we can so these phenomenological equations are determined properly, so they obey a particular action, a general action that's well understood, and their integration describes the timing precisely. So we don't see the kinds of effects that Archibald et al. Saw in their paper, and we get a better limit from the on the limit on the on violation of the universality of free fall. You just get a better limit. However, the thing is, this came at an enormous observation cost. So you can see here, the observations are almost daily for many months on end with the Nancy telescope. The only reason why this is possible is because this is at a right ascension that is very poorly, where there's not much anything else to see. You can see here, like the T waves as a function of Earth orbital phase, outer orbital phase of the outer system, which is 327 days, and also inner orbital phase. There's a gap there around 300, just when the system is behind the sun. Anyway, you see the amounts of data that are necessary. So the timing is for these things is so intense that we know of another triple system, B1620-36, which is located in globular cluster M4, which has not been followed at all for decades now. And this is a real pity, because then we never determine properly a full set of masses and orbital parameters for this system. because there's no available timing, and people cannot follow it up, and no proper arguments. So on top of that, we recently found that some of our eccentric millisecond pulsars are likely members of very wide triple systems. Again, this was only found because we had prolonged timing that was aimed at measuring their masses, and it was because of that we found those things. So this is the conclusion that makes me think that Argos should lead to the discovery of many more triple systems. So my summary is here. I think the conclusions are obvious. So daily Argos timing of normal pulsars will like finding many binary pulsars, including possibly a pulsar black hole system. It will expand. It will be great for following up and timing wide binary systems without any other considerations. I mean, this is a very absolutely clear. And it will help discover additional triple systems among the currently known binaries, and this will greatly increase the cadence and the timing of the known triple systems. So, yeah, that's it. Yeah.
So thank you very much, Paulo, also for being a perfect timer. So any questions for Paulo? So I do have a question, Paulo. Actually, I do have several questions, but I probably can take some of them offline. But one of them is regarding the eccentric MSPs that you mentioned. Is this does this refer to the MSPs with white dwarf companions, or is it something else?
Yeah, so these are the systems with white dwarf companions. So so there's a class of about 5 or 6 binary pulsars that are not well understood. So where you have like a millisecond pulsar with a white dwarf companion, and the normal stellar evolution scenarios would predict that the orbit is circular for these systems, and that is what we observe on hundreds of them. We see hundreds of them. We deal with the orbital eccentricities of the order of 10 to minus 6, 10 to minus 5, which is more or less what is predicted for these kinds of millisecond pulsars with white dwarf systems. In the last few years, we have been seeing several of these systems that have orbital eccentricities of the order of 0.1, and one of the possible explanations is that there have been several papers. One of them, I had a paper with Thomas Tauris about the possible origin of this, which is the collapse of a massive white dwarf, and that forms the millisecond pulsar. So these would give you the right eccentricity. John Antoniadis also had he's on a couple of theories actually on the formation of these objects, yeah. So that has been the case until now. A possibility that we are kind of discounting, because these systems all have orbital periods between 22 and 32 days. So the orbital eccentricities are always the same. Is that we thought it's kind of a uniform process. So it's not a chaotic process like disruption of a triple system. But it turns out that 2 of them now show very large variation of the orbital period and orbital frequency derivatives. So at least an F2, a large F2. This is clearly giving us an indication that there is a nearby object. I mean, by nearby, I mean at least hundreds of AU, but that there is likely, and that might have something to do with the formation of these eccentric systems, or at least a couple of them. For the others, there's no evidence of such a thing. So, yeah. But this is the thing. So we know that for these 2 particular systems, because we're timing these binaries, because we thought they were interesting, there could be some other circular binaries out there that no one cares about, that they're not especially interesting. And if you time them now, you might find that they also have these kinds of companion, So that is that's something where I think the the timing will with Argos would be very extremely useful.
Okay, so thank you very much, Paulo. Okay, I see one Golam has his hand raised. So Golam, you can go ahead and ask your question.
Hi, Paulo. That was an amazing talk. Just a quick question. So are you saying that it's okay to have daily monitoring, even if it's a less sensitive TOA per day, as
Yeah.
opposed to...
So the thing is, if even if you're not sensitive, I mean, you can find. So this is why I didn't go to systems like the double pulsar. You know, the double, of course, in double pulsar we have amazing timing and so on, but without knowing in detail what kind of TOA precision we get from Argos, I cannot say anything. I cannot say anything about how much that would improve our test of GR. These three things that I mentioned do not depend on the specific TOA precision. They just depend that you actually measure a TOA. And that is the thing, you know, like finding out about these binaries. I mean, in the triple system, of course, it matters. But the thing is, so finding about hidden binaries, you don't need TOA precision from that. And for many long period pulsars, it's better to have many TOAs, even if they're low precision, spread over time, than just having a few very precise TOAs that are not not very well spread in orbital phase, and they don't have much time or baseline coverage. So these are cases where it does not depend on the TOA precision, these effects. And the triple system, I think it's obvious. Like if you can get daily TOAs for this thing, I mean, it's going to improve things, even if they're not as precise. Even because, and that's another thing I didn't mention, many pulsars are scintillating. So if you look at them every day, you will see all the times where they appear strong, and then it's like you have a much larger telescope, right? So yeah. So yeah, a lot of these things are. I mean, the same thing for 1620. If you had TOAs with 1/10 of the precision of the GBT, but across all the time until now, you would have figured out the orbit and the masses of the objects to some precision.
Okay, so thank you very much,